Good morning, good afternoon, and good evening to everyone who joins us from around the world.
We're so glad you're here.
This is Andrew.
And Renee, welcome to the Stacks series.
Today we are exploring the physics of life.
Which I know sounds like an absolute contradiction in terms.
Yeah.
Usually when we talk about life, we are firmly planted in the biology department, right? We talk about natural selection, we talk about genes, DNA, the survival of the fittest. We think about wet, squishy, organic things.
Right, exactly. We tend to think of life as this messy biological miracle that somehow sits completely apart from the rigid, cold mathematical laws of the physical universe. Like physics is for billiard balls and gravity and planets, and biology is for plants and people. But today we are flipping that script entirely.
We really are. We're looking at an extensive stack of research today, papers from MIT, historical analyses of Nobel Prize winners, and some very bleeding-edge laboratory experiments that all point to a wild idea. The idea that life isn't just a biological phenomenon. It might actually be a physical inevitability.
And that is the core provocation of our entire exploration today. We are looking at the very real possibility that life is not some lucky cosmic accident, but the expected, mathematically predictable result of the fundamental laws of nature, specifically thermodynamics.
And I know that word can scare people off, but it's crucial. Because usually when you bring up physics to explain something as vibrant as life, it feels like trying to explain a beautiful painting by just listing the chemical makeup of the paint. It feels cold.
Yeah, strips the magic away. But the argument we are going to unpack today suggests that the math of physics doesn't just describe the painting, it actually painted it. Physics is the artist.
That is a big claim. So we should probably start by unpacking the central villain in the story, or, well, maybe the churro, depending on how you look at it. Entropy.
The second law of thermodynamics.
Right. The absolute law that the universe tends toward disorder.
So, for everyone listening, let's ground this. If I leave a hot cup of coffee on the kitchen counter, it cools down. It eventually reaches equilibrium with the room. Or if I build a highly structured sandcastle on the beach, the wind and the waves are going to knock it down. Things naturally fall apart.
Precisely. The second law states that in any isolated system, entropy always increases. Now, entropy is often casually described as disorder or messiness, but it's really about energy dispersal. The universe wants to spread energy out. It wants to distribute heat until everything everywhere is just a uniform, lukewarm soup. That is the ultimate drive toward maximum entropy.
Okay, hold on. I need to clarify that because I always remember entropy being explained as just messiness. Like my office gets messy.
Yeah.
If I don't actively organize my desk, papers end up in a chaotic pile. But you're talking about energy dispersal. Are those actually the same thing? Because a messy desk doesn't feel like a lukewarm soup to me. It just feels like I need to clean up.
That is such a common point of confusion, and it's important we distinguish the two before we go further. When physicists talk about entropy, they aren't just talking about visual clutter. They're talking about the statistical probability of energy states.
Okay, statistical probability. How so?
Think of it this way. There are billions and billions of ways for the air molecules in the room you are sitting in right now to be scattered randomly, bouncing off each other. But there is only one way for them to all be packed perfectly into a single corner of the ceiling.
Right, which would be very bad for anyone trying to breathe in that room.
Exactly. Nature chooses the state with the most possibilities, the most probable state. And mathematically, that state corresponds to energy being spread out, dispersed, and shared among all the particles.
Okay, so nature prefers the spread out state simply because it's statistically inevitable.
Yes. And that right there brings us to the massive, glaring paradox of our existence. You look at a living cell, or a giant redwood tree, or a human being, and we are incredibly ordered. We are the exact opposite of spread out. We are highly structured, deeply complex machines that somehow maintain that tight structure against the chaotic forces of the universe.
If the universe desperately wants to destroy order and disperse energy, I shouldn't exist. I should dissolve into my environment. So the central question we are tackling today, our mission for this entire discussion, is how does life exist without breaking the laws of physics? How do you get this localized island of intricate order in a universe that is hell-bent on chaos?
And the answer, which we are going to explore in our foundation section, is that life doesn't actually violate the second law of thermodynamics. In fact, the prevailing argument from brilliant physicists like Jeremy England and Ilya Prigogine is that life is the result of the second law.
Meaning life is a tool for the universe.
Yes, life is a remarkably efficient way to scatter energy into the universe.
I have to be honest, that sounds a bit convenient. It almost sounds like we're just creatively redefining the word life to make the math work out. If a hurricane dissipates energy, and I dissipate energy, are you seriously saying the only difference between me and a weather event is just the level of complexity?
It does challenge our ego, doesn't it? It strips away the biological exceptionalism, but it replaces it with a profound cosmic connection. It suggests that you, the hurricane, and the nearest star are all playing the exact same physical game, just at vastly different scales. We aren't fighting the universe. We are the universe's way of solving a thermodynamic problem.
Okay, I'm skeptical, but I'm absolutely fascinated. We are the universe's way of solving a problem. Let's keep that framework in mind as we organize this information. We have a ton of ground to cover. We're going to start chronologically with the foundations, the history of how science thought life began, and how physics entered the chat.
Then we'll move into the active debate about where this actually happened on early Earth, the primordial soup versus the deep sea vents.
Right, and finally we'll dive into the frontiers, which is where the source material genuinely blew my mind. We're talking about synthetic oil droplets solving physical mazes and robotic chemistry.
It is a wild journey from the absolute beginning of Earth's history to the future of artificial lab-grown life.
So let's jump right into part one. Foundations. What we think we know about the origins of life. Now, when most people talk about how life began, the classic image that comes to mind is the primordial soup.
Yeah, the famous Oppenheim hypothesis. This goes way back to the 1920s. The idea was that the early Earth had a reducing atmosphere, meaning it was full of gases like methane, ammonia, and hydrogen, but no free oxygen. And there was this warm little pond, which is a term Darwin actually coined.
And this theory led directly to the famous Miller-Urey experiment in 1952. If you took high school biology, this is the one picture you definitely saw in your textbook, the crazy glass tubes and the sparks.
It's an iconic piece of science history. Stanley Miller and Harold Urey were essentially trying to take a baby photo of the Earth. They wanted to recreate those exact early conditions. So they put those simple gases, the methane, ammonia, and hydrogen, into a sealed glass flask. They added boiling water to simulate the hot, ancient ocean, and then, crucially, they introduced electrical sparks.
To simulate lightning storms on the early Earth.
Exactly! Lightning striking the primordial soup. And they just let the whole contraption run.
And it was a massive success, right? They created the building blocks of life in a lab.
They did. After just a week, the clear water turned this bright pink color and then eventually a murky brown. When they analyzed that brown sludge, they found amino acids, which are the fundamental building blocks of proteins. It was a global headline. It essentially proved that you can get organic biological molecules purely from inorganic dead chemistry. You don't need a divine, mystical spark. You just need a literal electrical spark.
But, and this is a huge, but that I feel like gets totally glossed over when we learn about this in school, there is a massive, almost incomprehensible gap between having a murky flask of amino acids and having a living, breathing cell.
Oh, it is a canyon of a gap.
The sources refer to this as the improbability problem.
Right. As the research notes point out, creating the basic building blocks is actually relatively easy. We find amino acids on random meteorites floating in space now. But assembling those loose blocks into a functioning, self-replicating cell, that is a completely different beast.
I love the analogy they used in the text from the astrophysicist Fred Hoyle for this.
The tornado in the junkyard?
Yes. The idea that expecting random amino acids to bump into each other and accidentally form a living cell is like expecting a tornado to tear through a scrapyard and perfectly assemble a fully functional Boeing 747 airplane.
It really puts the scale of the problem into perspective. You can have all the raw materials you want, the aluminum, the glass, the rubber, which represent our amino acids, but a tornado, representing random chance and time, isn't going to build a jet engine. The statistical probability of random chemicals in a warm pond bumping together to form a complex ribosome or a strand of DNA is effectively zero. Even if you give it billions of years, the math simply does not work out. The sheer complexity is too high.
So if random chance is too slow and statistically impossible, and we are ruling out magic, there has to be a mechanism we're missing. There has to be a driving force pushing those pieces together.
And that is exactly where physics steps in to save biology. If the tornado can't build the airplane by accident, maybe there is a fundamental law of physics that actively forces the junk to organize itself. This is where the narrative shifts to a physicist named Ilya Prigogine and his concept of dissipative structures.
And Prigogine actually won a Nobel Prize in chemistry for this work in 1977. So this isn't some fringe internet theory. This is established science. But the term dissipative structure sounds terrifyingly technical to me. Can you break that down for us?
Let's go back to our earlier point about the universe wanting to reach equilibrium. It wants everything to be the same, flat temperature. But Prigogine showed that when a system is driven far from equilibrium, meaning when you pump a massive constant flow of energy into it, it doesn't just get more chaotic. Under the right conditions, the system will spontaneously organize itself to dissipate that incoming energy faster.
Okay, I'm going to need a real-world example of that, something I can visualize.
Absolutely. The classic textbook example is something called Bayard cells. Imagine a thin layer of oil or liquid in a flat frying pan. You put it on the stove and heat it from the bottom.
Okay, I'm picturing the pan on the stove.
At first, when the heat is low, the thermal energy just conducts straight up through the liquid randomly. But if you crank up the heat, you create a very steep temperature gradient between the hot bottom of the pan and the cooler air at the top. Suddenly, the liquid undergoes a massive shift. It stops moving randomly and organizes into these perfect geometric hexagonal convection cells. It literally looks like a honeycomb made of moving fluid.
Wait, the liquid just spontaneously creates a honeycomb pattern.
Yes. Millions and millions of individual molecules suddenly coordinate their movement to roll up and down in these microscopic hexagonal tubes.
Why? Does the oil somehow want to be a hexagon?
Not at all. It happens because that specific hexagonal structure is mathematically the most efficient way to physically transport the heat from the hot bottom to the cool top. The chaos of the extreme heat literally forces the liquid to become ordered so it can get rid of the energy faster. The order is just a mechanism for dissipation.
Okay, that clicks. That makes sense.
Yeah.
And a hurricane operates on the same principle, right?
Exactly the same principle, just on a planetary scale. A hurricane is a highly ordered, terrifyingly beautiful structure. It has an eye and eye wall, spiral rain bands. It looks like it was designed by an engineer, but it is spontaneously created purely to dissipate the massive heat difference between the warm ocean surface and the freezing upper atmosphere. The order only exists because it destroys that temperature gradient faster than chaotic random winds could.
So nature actually builds complex structures just to dump heat. And the argument here is that life, that you and I are just very, very complex Bayard cells.
Essentially, yes. And this is where a modern physicist named Jeremy England enters the picture. His work, much of it done while he was at MIT, has been dubbed the new physics of life. He takes Prigogine's macroscopic idea of the frying pan and the hurricane and applies it down to the microscopic atomic level. He argues that the distinction between living matter and dead matter isn't a sharp line at all. He proposes a concept called dissipation-driven adaptation.
Dissipation-driven adaptation. I remember reading his analogy about the rock rolling downhill to explain this.
Yeah, it's a great analogy. He says that the origin of life should be as utterly unsurprising as watching a rock roll down a steep hill. When we see a rock at the bottom of a valley, we don't look at it and say, wow, what a statistical anomaly. How did it ever find its way down here? We know that gravity pulled it there to lower its potential energy. England argues that if you have a clump of carbon atoms and you shine a bright light on it for a few billion years, it shouldn't be surprising at all if it eventually organizes into a plant.
See, that sounds insane to me. A plant from a random clump of atoms, just because I shine a light on it.
I know it sounds wild, but let's think about it thermodynamically, using another analogy from the sources. Have you ever seen an opera singer hit a high note and shatter a wine glass?
Yeah, of course. They hit the exact right pitch, the glass vibrates uncontrollably, and it shatters.
That is acoustic resonance. The physical structure of the glass is forced to absorb the energy of the sound waves until it literally cannot hold its shape anymore, and it breaks into a new arrangement of shards. Now, imagine you have a microscopic pile of unorganized atoms. You hit them with a constant, relentless flow of energy-like intense sunlight. Most random arrangements of atoms are pretty bad at absorbing that specific frequency of light. They just get a tiny bit warm and reflect the rest.
Okay, following so far.
But if those atoms happen to bump into a new configuration, if they break and rearrange like the glass into a shape that resonates better with that solar energy, they will lock into that shape. Over millions of years, the matter will continually shift and adapt into whatever shape is best at absorbing the energy and violently scattering it as heat. England calls this dissipative adaptation. The physical matter adapts to the energy flow.
So what you're saying is a tree is just a configuration of atoms that is really, really good at catching sunlight.
A tree is an incredible machine designed by the laws of physics to capture high-energy solar photons, use that energy to build more structure to catch more photons, and then radiate the waste energy away as low-grade heat. A tree is much, much better at increasing the entropy of the universe than a pile of dead dirt is. The dirt just reflects the light back into space. The tree actively grabs it, degrades it, and scatters it.
So nature selectively favors this structure that is best at making a thermodynamic mess.
Exactly. England argues that matter naturally self-organizes to resonate with whatever the driving energy force is. In Earth's case, that's the sun. Life is just the undisputed champion of energy dissipation. We are all just excellent heat sinks.
It definitely takes a bit of the romance out of the human experience, doesn't it? Like, you can't exactly look at someone and say, darling, you are the most efficient dissipative structure I've ever met.
It might not be poetry, but it is deeply unifying. It suggests that biology is really just a highly specialized sub-branch of physics. It bridges that impossible gap between the rock and the rose. They are both just obeying the same master.
Okay, so if physics provides the motive, the ultimate thermodynamic why life happens, we still have to figure out the actual how, the nuts and bolts mechanism. Because even if the universe desperately wants a biological heat sink, it still has to physically build one out of raw chemicals. And this brings us perfectly into the active debate section of our discussion. Where did this physical assembly actually happen?
Right. Earlier we mentioned the soup Darwin's warm little pond. But as we got better at understanding ancient chemistry, a massive problem emerged with the soup theory.
The dilution problem. I remember this from the reading.
Yes. The ocean is incomprehensibly huge. If you have one tiny amino acid floating in the primordial Pacific Ocean and another one floating in the ancient Atlantic, they are never, ever going to meet to form a protein chain. The math of random collision fails again. It's incredibly hard to get individual molecules to consistently interact when they are diluted in a billion cubic miles of water.
So the scientific pendulum has swung aggressively toward a different location, hydrothermal vents.
Specifically, deep-sea alkaline hydrothermal vents. Now, these are different from the super hot, highly acidic black smokers you might have seen on nature shows. These are white smokers. And these environments are an absolute gold mine from a physics perspective.
Because they provide a gradient, right? We keep coming back to this idea of gradients in energy flow.
Exactly. Life fundamentally requires a difference in energy to run. It needs a high and a low to flow between. Down at these vents, deep under the ocean, you have hot, highly alkaline, mineral-rich fluid jetting out of the Earth's crust, immediately meeting freezing cold, acidic ocean water. So right there, you have an extreme temperature gradient and a severe chemical pH gradient.
And the physical structure of the vent rocks themselves is totally unique. I was reading that they aren't just solid, dense rocks. They are porous.
They are essentially giant mineral sponges. They are packed with millions of tiny, interconnected, microscopic chambers that are roughly the exact size of a biological organic cell. So suddenly, this solves the dilution problem. You have a natural geological flask that traps and concentrates the chemicals together so they can interact. And you have a constant, endless flow of geothermal energy rushing right through them. One of our sources extensively detailed how early life likely utilized something called chemiosmosis in these pores.
Let's unpack that. Chemiosmosis is a $10 word. What exactly is that doing?
At its core, chemiosmosis is just the movement of ions across a semi-permeable membrane to generate power. It is literally the exact mechanism that your cells use right this second to generate ATP, which is the energy currency of your body. Our modern cells have incredibly complex protein pumps embedded in our membranes that push protons back and forth to create a charge difference. The vent theory suggests that long before life was smart enough to invent its own organic membrane and its own protein pumps, the porous rock itself acted as the membrane, and the natural pH difference of the vent provided the free flow of protons.
So the Earth itself acted as the first battery for life. The rocks provided the hardware.
That is a brilliant way to conceptualize it. The geological structure of the vent did all the heavy lifting. The matter just flowed into the pores, adapted to dissipate the energy gradient, and started using the free geothermal electricity.
That makes so much sense. It elegantly solves the energy problem and the location problem.
Yeah.
But what about the information problem?
Yeah.
The biological chicken or the egg situation.
Yeah.
We have this massive conundrum with DNA and proteins.
Ah, yes. The classic biological paradox. In all modern life, DNA holds the genetic blueprint, the instructions needed to build proteins. But you absolutely need proteins, specifically enzymes, to physically read the DNA and replicate it. One cannot function without the other. You can't have the factory without the blueprints, but you can't read the blueprints without the factory workers. So which one possibly came first?
The leading contender for a long time, at least according to biology textbooks, has been the RNA world hypothesis.
Right. RNA is a molecular cousin of DNA. But unlike DNA, which is mostly just a passive storage hard drive, RNA is flexible. It can fold up into complex three-dimensional shapes and act like an active enzyme. It can actually catalyze chemical reactions. Biologists call these ribozymes. So the prevailing idea was, first came RNA, which could both store the information and do the physical copying work itself, and then DNA and proteins evolved later as specialized upgrades.
But the sources presented a very strong rival theory, right? The metabolism first hypothesis.
Yeah.
And honestly, this one feels like it fits our whole physics and energy theme much better.
It absolutely does. The metabolism first hypothesis suggests that long before there were any complicated genetic codes or RNA blueprints, there was just a raw, self-sustaining cycle of chemical reactions. Physicists refer to this as an autocatalytic set.
Autocatalytic set. I saw that term heavily featured in the Templeton Foundation source we reviewed. But again, it sounds incredibly dense.
It sounds dense, but the underlying concept is beautifully simple. Imagine a small, isolated, medieval village economy.
Okay, I'm listening. Paint the picture.
You have three people, a blacksmith, a carpenter, and a farmer. The blacksmith forges tools and gives them to the carpenter. The carpenter uses the tools to build a sturdy barn for the farmer, and the farmer uses the barn to store wheat, which feeds the blacksmith.
Right, it's a closed dependency loop.
Exactly. It's a self-sustaining loop. If you remove the farmer, the blacksmith starves, no tools are made, and the whole economy collapses. But working together, the system sustains itself. It can even grow. And notice, it doesn't have a king or a boss, which would be the DNA in this analogy, dictating what everyone does. The raw flow of goods, or in chemistry, the flow of energy and matter, keeps the cycle spinning.
So the theory is that simple chemicals at the bottom of the ocean formed these microscopic village economies first.
Precisely. Chemical A reacts to create chemical B, B creates C, and C loops back around to help create more of A. As long as the hydrothermal vent keeps pumping thermal energy and raw materials into the system, the chemical cycle spins faster and grows. It essentially evolves. If a new random molecule, let's call it chemical D, drifts in and makes the whole cycle run more efficiently, the chemical village naturally incorporates it.
So life literally started as a blind chemical engine, not as a library of genetic information.
That is the core argument of the metabolism first camp. And what's fascinating is that researchers today are finding the remnants of these exact autocatalytic sets hidden deep inside the metabolic networks of actual living organisms. It heavily implies that the energy engine came first, driven by thermodynamics, and the genetic blueprint evolved much later just to optimize the engine.
Which brings us perfectly to the ultimate question of luck. Is the existence of life just a frozen accident? Was the formation of that very first functional ribosome just a lucky 1 in a trillion roll of the cosmic dice?
Well, if you ask traditional evolutionary biologists who focus strictly on the baffling complexity of the genetic code, they often lean toward the frozen accident theory. They look at the sheer intricacy of DNA and say, it is so specific, it might have only happened once in the history of the universe.
But if you ask the thermodynamic physicists like Jeremy England,
they say it is an absolute inevitability. If you have the right energy flow, whether it's sunlight hitting a rock or a thermal vent pumping out heat, and you have the basic raw materials, the matter will self-organize. It is not an accident. It is a guaranteed phase transition. Think about water turning into ice. You don't need luck for water to freeze, you just need the temperature to drop below zero. England argues life is the exact same type of physical inevitability.
that is a profound, almost dizzying shift in perspective. Because if life is just a predictable phase transition driven by thermodynamics, it means we aren't a lonely anomaly. It should be happening everywhere in the cosmos.
We will definitely get to the implications for alien life in a bit. But first, I want to talk about how scientists are actively testing these wild ideas right now. Because we aren't just theorizing and looking at ancient fossils anymore. We are literally building alternative life forms in the laboratory. And this is where the research gets genuinely science fiction.
Yes, this brings us to the frontiers section of our exploration. And this is where the sources completely blew me away. Because we are moving entirely away from the standard DNA and protein model of biology, and we are looking at, well, we're looking at droplets.
Oil and water droplets. I know it sounds like we're making a simple salad dressing, but it is the absolute cutting edge of abiogenesis research right now.
The source titled Droplets, Unconventional Protocell Model was fascinating. It specifically talks about something called orthologous life. What does that actually mean in this context?
Orthologous life means a completely different, parallel way of being alive. It means we aren't just trying to reverse engineer and mimic the carbon-based biology we already know. We are finding a completely separate track to life. These experimental droplets do not have DNA. They don't have a single protein, but they behave exactly like living cells.
The behavioral examples in the paper were crazy. They documented droplets that can literally solve a physical maze. How on earth does a microscopic drop of oil solve a maze? It obviously doesn't have a brain or a nervous system.
It does it purely through physics, specifically something called the Marangoni effect.
Okay, stop right there. The Marangoni effect. I need to visualize this. How does that work?
Okay, think about a glass of strong wine. You know when you swirl the wine and those little droplets form on the inside of the glass and slowly drip back down? They call them the tears of wine.
Yeah, I've seen that.
That phenomenon is caused by a difference in surface tension between the alcohol evaporating and the water left behind. Or, to make it even simpler, try this mental experiment. Imagine a tiny little toy boat made of cardboard floating perfectly still in a sink full of water. If you drop a single drop of liquid dish soap into the water right behind the boat, what happens?
The boat violently shoots forward. I actually used to do that trick when I was a kid.
Exactly. The soap immediately lowers the surface tension of the water right behind the boat. The pure water in front of the boat still has very high surface tension, so it physically pulls the boat forward. That forceful pull is the Marangoni flow in action.
So these synthetic oil droplets are acting like little microscopic soap boats.
Yes, exactly. If you place one of these specialized droplets into an environment with a chemical gradient, say a microscopic maze where there is a trail of salt or a slight pH change leading to the exit, the surface tension on one side of the droplet changes relative to the other side. This creates an internal Marangoni flow that literally pushes the entire droplet forward. In biology, we call this movement chemotaxis.
So the droplet is physically sensing the chemical path and intentionally moving along it.
In a mechanical sense, yes.
Yeah.
In the maze experiment, the chemical gradient acts exactly like a scent trail. The droplet navigates all the twists and turns to find the exit, not because it is consciously thinking, but because it is blindly following the thermodynamic path of least resistance.
Yeah.
It naturally finds the downhill slope in the chemical landscape to dissipate the energy.
And the research said they can also hunt.
Yes. Researchers have observed clear predator and prey behaviors. They engineered one type of droplet that is chemically drawn to another type. So you have a predator droplet actively chasing a prey droplet around a petri dish because of the continuous chemical interactions between their surfaces. And it gets crazier. They can even reproduce.
How does an oil droplet reproduce?
If a droplet consumes enough chemical fuel from its environment and gets physically too large, the internal chemical dynamics become unstable. The surface tension breaks down, and it spontaneously splits into two perfectly formed daughter droplets.
Okay, let's tally this up. We have self-propelled movement, we have actively sensing the environment, we have reproduction, and we have consuming fuel to survive. That ticks almost all the major boxes for the definition of life.
And yet it is literally just oil, water, and some basic surfactants. It entirely challenges our fundamental definition of biology. Earlier we mentioned NASA defines life as a self-sustaining chemical system capable of Darwinian evolution. These droplets are undeniably self-sustaining active matter.
So putting the pieces together, nature likely used the rocky vents as a crutch, a pre-made geological battery, to get the engine started. But eventually, if life was going to spread, it had to leave the vent. It had to figure out how to package that chemical fire inside a mobile membrane. And that brings us to the most futuristic part of the reading stack. We are actively trying to recreate that exact transition moment in the lab right now. We are trying to package that thermodynamic fire into artificial cells.
Which moves us firmly into the realm of synthetic biology. Because we aren't just passively observing oil droplets anymore, we are aggressively utilizing robotics and artificial intelligence to map out what chemists are calling the dark net of chemistry.
The dark net of chemistry. I love that term, but it sounds incredibly ominous, like a place where I would go to buy illegal stolen passwords.
Right, but in this scientific context, the dark net is the vastly unexplored, practically infinite web of possible chemical reactivity. Think about how chemistry is traditionally done. A human chemist usually looks for a very specific linear reaction. They want chemical A plus chemical B to yield chemical C. They have a known target. But the universe of potential chemical combinations is staggeringly vast. There are billions of weird, complex, nonlinear chemical interactions we've simply never tested because no human had a specific commercial or biological reason to.
So they're unleashing AI and automated robots to just run thousands of blind experiments.
Exactly. The AI isn't looking for a specific drug or material. It is just exploring the dark map. It is explicitly hunting for those autocatalytic sets we talked about earlier, those self-sustaining village economies. It is looking for hidden, chaotic pathways where chemicals spontaneously start to boost each other's production in closed loops. The ultimate goal is to discover entirely synthetic chemical systems that start to act alive, systems that adapt to sudden changes, repair their own structures, and evolve without using a single piece of standard DNA.
And this extensive AI research leads directly to the concept of animate matter.
Yes, that's a key term pulled straight from the active matter roadmap source we reviewed. Animate matter. These are engineered materials that completely blur the boundary between object and organism. Imagine constructing a suspension bridge out of animate concrete that can actively sense microfractures and physically heal its own cracks using ambient energy. Or a medical drug delivery system that isn't just a dumb, passive pill you swallow, but a coordinated swarm of synthetic, microscopic worms that actively swim through your bloodstream, navigating the vascular maze to hunt down a specific tumor.
The source material specifically mentions synthetic worms, and I have to admit that sounds like the plot of a terrifying sci-fi horror movie.
It sounds scary, but it is potentially revolutionary for medicine. These worms are three-dimensional physical structures that are entirely driven by what we call dissipative self-assembly. The best way to understand this is to picture a large water fountain.
Okay, I have a water fountain in my head.
When you look at the fountain, the grand shape of the water, the beautiful arching curves, looks solid and static. It holds a distinct, recognizable form. But the actual water molecules making up that shape are constantly changing. They are moving at high speed. The physical structure of the fountain only exists because a pump is continuously forcing energy and water through it. If you cut the power to the pump, the beautiful shape instantly collapses into a flat puddle.
Right. Contrast that with, say, a plastic Lego castle. I build the castle, I walk away, and it just stays there forever. It requires zero energy input to maintain its structural integrity.
Precisely. The Lego castle represents static equilibrium. It is dead matter. The water fountain represents a dissipative structure. And the mind-bending reality is that you, sitting there right now, are a fountain.
I am a water fountain.
Thermodynamically, yes. If you stop eating food, if your cells stop metabolizing fuel, you quickly reach equilibrium with your environment. You die. You decay and dissolve. Your highly organized physical structure only exists because a constant river of energy is flowing straight through you. These synthetic worms built in the lab operate on the exact same principle. They must constantly consume chemical fuel from their surrounding environment to maintain their physical shape and to move. They are literally animate.
So we are fundamentally crossing a threshold here. We are moving from merely describing how life works to actively constructing it from scratch. That feels like a massive, irreversible threshold for humanity.
It truly is, and it provides a perfect pivot to the final section of our outline, the implications. Because we have to ask, why does all this dense physics and chemistry matter to the listener? If someone's listening to this in their living room, how does this change their worldview?
Well, the first major implication is the massive philosophical shift. If Jeremy England and the thermodynamic theorists are correct, we aren't some magical, delicate exception to the harsh rules of the universe. We aren't biological rebels fighting against the cold, dark cosmos.
No, not at all. We are the ultimate, perfect expression of the cosmos's deep desire to release energy. It connects us back to the stars in a very literal, physical way. Think about the chain. A giant star burns nuclear fuel and radiates intense light. That light travels through empty space and hits a wet rock called Earth. The dead matter on that rock is forced to self-organize into complex things like algae, redwood trees, and eventually human beings, solely to catch that incoming light, degrade it, and efficiently turn it into waste heat. We are an integral part of the universe's energy flow.
I have to admit, it makes me feel strangely, well, useful. In a grand, cosmic sort of way, I am a very efficient heat sink. But I do have to ask the dark question here. Does embracing this physics perspective make human life less special? If my entire existence is just the equivalent of a complicated rock rolling down a thermodynamic hill, is there any actual room left for human agency, for free will, for art or music or love? Or is all of that just a byproduct of heat dissipation too?
That is the ultimate existential question that this research provokes. But I would strongly argue that this perspective makes us incredibly more special. The universe has these rigid, blind laws: gravity, electromagnetism, thermodynamics. Almost all matter in the universe just obeys them blindly, as dead rocks or burning gas. But here on Earth, the universe has blindly built a dissipative structure so staggeringly complex, the human brain, that it can actually wake up, look around, and understand the mathematical laws that created it. We are the universe literally waking up to itself.
Okay, I genuinely like that framing. I much prefer being the universe waking up to itself rather than just a biological heat sink. Now, let's pivot to something practical. Aliens. Because this thermodynamic definition of life completely changes the search for extraterrestrial life, doesn't it?
It expands the search parameters entirely. Historically, astrobiology has been obsessed with the Goldilocks zone. We look for exoplanets that have liquid surface water and mild Earth-like temperatures. We essentially look for carbon copy versions of us.
But if life is fundamentally just about dissipation-driven adaptation, as the physics suggests, it could theoretically emerge anywhere in the universe where there is a sustained energy gradient.
Exactly. Just look at Titan, one of Saturn's largest moons. The surface is freezing cold, well below -200 degrees. There's absolutely no liquid water, but it has massive flowing lakes and rivers of liquid methane and ethane, and crucially, it has active energy gradients.
So under this new framework, you can absolutely have orthologous life like our synthetic droplets thriving on Titan.
Yes. You could have a thriving ecosystem of orthologous life that uses liquid methane as its solvent instead of water and completely ignores DNA. If we limit our expensive space telescopes to only looking for Earth-like biological signatures, we might literally be staring right at a massive alien ecosystem and completely fail to recognize it because it is actively dissipating energy in a way we aren't trained to see.
The sources emphasize that redefining life as a thermodynamic process expands our search radius from a few lucky planets to potentially millions of moons and rogue planets.
It does. And beyond the search for aliens, there are massive terrestrial economic implications. We touched on this briefly with the animate matter concept, but think about the future economy of manufacturing.
Sustainable manufacturing. This was a huge point in the active matter roadmap.
Biology is so incredibly efficient at manufacturing. A microscopic plant cell can build incredibly complex, durable carbon structures at room temperature using the most common elements on Earth with virtually zero toxic waste. Meanwhile, our human factories require massive amounts of electricity, extreme heat, high pressure, and they produce devastating toxic runoff.
So if we can truly master this principle of dissipative self-assembly, we can revolutionize how we build everything. We can manufacture materials the exact same way nature does.
Exactly. We are talking about ushering in an era of smart materials that autonomously adapt to their environment. We mentioned the self-healing concrete. We are talking about advanced medicines that act as hunting swarms, like those chemotactic droplets tracking a chemical scent. We are looking at a near-future fusion of digital AI, synthetic chemistry, and biological efficiency.
It really fundamentally blurs the lines of reality. I mean, if you engineer a synthetic robot made entirely of soft chemical gels, and it can actively sense its environment, autonomously solve a maze to find fuel, and physically repair its own damage using ambient energy, is it a machine or is it a living creature?
That is going to be the defining ethical and scientific question of the 21st century. As we continue to build these synthetic protocells in animate matter, the rigid distinction we've always had between what is alive and what is not alive is going to completely vanish. It is no longer a binary switch. It's going to become a very wide spectrum. A dead rock is at one far end, a conscious human being is at the other. But right in the murky middle, there is going to be a vast new domain of active, animate matter that completely defies our traditional categorization.
It is an overwhelming amount of information to process. We started with ancient lightning in a flask and ended up with AI-designed synthetic worm swarms.
It is a lot, but I also find it deeply hopeful. We culturally often think of life as this incredibly fragile, delicate candle flame flickering in a cosmic gale ready to be blown out at any moment. But if the thermodynamic hypothesis is correct, life isn't the fragile flame fighting the gale. Life is the fire that actively feeds on the gale. It is robust. It is mathematically inevitable.
I really love that visual. Life as an inevitable fire.
Every single living thing is literally on fire, slowly burning, as Jeremy England puts it. We are all constantly burning through energy just to stay physically organized.
So synthesizing all of this, what is the ultimate takeaway here? For me, reading through all this research, it's the realization that the fundamental laws of physics aren't just rigid constraints. They aren't just invisible walls that biological life occasionally bumps into. They are the actual engine of creation. They are the builders.
And it proves that the deep mystery of our origin isn't some untouchable miracle that we can never hope to understand. It is a tangible physical puzzle. And it's a puzzle we are actively, relentlessly solving right now. One synthetic droplet, one thermodynamic equation, and one robotic experiment at a time.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. We hope you enjoyed today's discussion. If you did, be sure to subscribe and support us in Patreon. And of course, you can write to us in comments if a specific topic needed to be covered, which help us all to grow.
One last thought to leave everyone with. If we truly are just incredibly efficient entropy machines designed by thermodynamics to disperse energy, does that technically mean by staying alive and building complex societies, we are actually accelerating the inevitable heat death of the universe?
Well, yes. Thermodynamically speaking, the better we get at surviving and consuming energy, the faster we bring about the end of the cosmos.
Wow. Okay, I'm going to need a long time to process that. We are the universe's way of rushing toward the finish line.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.